Hi, welcome to the Signal Path. In this episode, I have something really exciting to review, and that is the Keysight FieldFox Microwave Analyzer. Now, I've been wanting to review one of these for a very long time, and this is not just any FieldFox. This is a 50 gigahertz B revision model. Now, these actually go up to 54 gigahertz. That's the highest frequency range you can get in a single sweep, of course. Now, these are battery-operated, shock-resistant, intended for outdoor uses. But the specification of these instruments almost seem not real because they have a full two-port network analyzer, 120 megahertz real-time spectrum analyzer anywhere across its span, of course, full coverage of the spectrum analysis as well. And you also can do noise figure measurements with it. And you can wrap so much application around this. You can treat this almost like a software-defined radio with network analysis capability with independent synthesizers inside of them. The architecture of these things are marvels of engineering, and because you can wrap so much software around it, these things have tons of options, so you can solve all kind of problems out in the field. That includes even over-the-air measurements of phased arrays and phased array controls. These things are just incredible. Now, there's a lot to talk about. I'm going to do a bunch of experiments with them so you can at least see what is going on, but I'm only going to be able to cover really a fraction of its capabilities. Nonetheless, I hope you enjoy this and we can do some cool things with it. And here's the Keysight FieldFox up close and personal. This is the microwave analyzer, which has both the network analyzer and spectrum analyzer capability. This is also fully loaded, so there are a lot of options to play around with. This is model N9952B. This is a 50 gigahertz model. It does go all the way up to 54 gigahertz, which then changes the connectors at the very top as well, and that's the highest frequency you can get in this form factor. Now, it is essentially built for outdoor use, not surprisingly, because of its form factor. It weighs about 7.35 pounds, and it has a strap here, which I haven't installed. It's fairly easy and comfortable to use. It does have a built-in battery, which is field replaceable, and it gives you about 4 hours of use time. Now, everything they've done here is to ensure that you can use it quickly and efficiently outdoors in the field. The buttons are fairly large. You can operate with a glove, of course. Everything is backlight. The screen is non-reflective, so that you can see it easily in the sunlight. It is also water resistant and fully enclosed, including all of its ports and the back, which I will show you in a second. It means that it can meet some pretty harsh environmental conditions. So it meets the MIL specification, if you really want to know, particularly the MIL PRF 28800F Class 2. It's also rated to operate from minus 10 degrees to plus 55 degrees Celsius, or 14 to 131 Fahrenheit. So because of the fact that it is intended for harsh environment, they've paid a lot of attention to also make it easy to use outdoors. So a lot of measurements and wizards are built into the software so you can make measurements quickly. Now, the wide frequency coverage means you can cover 5G frequencies, radars, satellite communication. It does have a GPS, of course, so you can survey and do over-the-air measurements. It does even have phased array control built into it. Everything to make it easy so you can do measurements quickly outdoor. Now, if you look on the right side over here, we have a couple of ports. When we open them, obviously everything has a door so that it is continuously protected against water. We have USB ports, we have micro SD trigger, we have an IF output, Ethernet on this side, and on the left we have our headphone jack, a DC output, which is going to be very, very handy. I'll show you that in a second. We're going to use it in a couple of our measurements, and of course the power to put the power in, so you can charge the internal battery. Now, this does have a fan in the back. Now, even though it has a fan, the unit is still fully enclosed. The fan is powered through the chassis with a connector, so you can remove the fan, and there is no way for water to get on the inside. They've thought of that, and I've actually never heard the fan run, but because it does have to operate up to 55 degrees Celsius external temperature, you can imagine under some circumstances that fan would certainly be required. On this unit, I have installed some connector savers in order to protect the 2.4 millimeter interfaces on the unit. Now, this is why it looks a little bit strange. These little caps here go directly on the built-in connectors, and they're fairly ruggedized nonetheless, but I like to protect them. They still end in a 2.4 millimeter interface, so we're not changing anything in terms of the frequency response. There is the antenna for the GPS and the reference connector at the very top as well. Now, because this is a fully loaded unit, it has real-time, it has spectrum analysis, it has network analysis with all the software options. There's essentially hundreds of different experiments we can do just to show you its capabilities. So I've selected a few so that you can see the unit in action, and you can see most of its strengths and some of its weaknesses, and then you can judge if it fits into your lab. Now, in order to make the recording of the screen and the instrument a little bit easier, I will use the remote interface software, which is a virtual view of the unit with all the buttons in exactly the same way. That software is freely available from Keysight's website. Now, there's one caveat with that. You just have to keep in mind that the refresh rate of the screen here is often quite a bit faster than the refresh rate of what you get from the virtual interface. Everything is going to be connected to the LAN, of course, but whenever it's appropriate, I will let you know. The FieldFox is of course a full 2-port network analyzer with all the functions you would expect to find in a full-size network analyzer. That includes quite advanced wizards to walk you through different calibration mechanisms here. So right now I've chosen an ecal. You can see the ecal over here on the left, and of course it has full support for ecals, which are connected directly to the USB port here on the right side. And it walks you through setting up the different connector types that you have on your device under test, ensuring that your calibration is accurate and that you're able to move the measurement plane to the edge of device under test. That's important because if you do that incorrectly, you think you've done your calibration, but actually your measurement plane is somewhere in the middle, and that can lead to inaccuracies. And with such a massive dynamic range of this instrument, that's important. So here we have the ecal already set up, and another nice feature is that if the power incident coming from the instrument is too high, for instance, for the ecal module or whatever calibration module you're using, it would warn you. So here it is telling me that the power that I have chosen for my incident is too high for this. So it allows me to lower that to make sure that the calibration is again accurate. You can also use other calibration standards. For example, like this one. This is my most expensive fidget spinner. This is a Keysight A5563A, which is a 50 gigahertz calibration standard where the open, short, and load are connected together in this form factor. And this just means that you don't lose them and you can easily find them eventually, and they age roughly at the same rate. And you can enter that information into the instrument and it will bring the calibration coefficients already built into the firmware. So ecal is of course quite convenient, and I've done videos on why that is, so we can go ahead and use this. First I'm going to do calibration, and then let's do some S-parameter experiments. So let's go ahead and try to measure a prototype reflection type phase shifter. Now phase shifters have become quite popular recently, primarily because of the wide use of phased arrays, where you need a phase shifter for each antenna in order to do electronic beam steering, and I've talked a lot about that in other videos. Now at the heart of a reflection type phase shifter, we have a 90-degree hybrid coupler. Now phase shifters like this have some advantages and some disadvantages. And primarily in this case, its advantage is that it can be made passive and have almost no power consumption. So here we have a 0 degree and a 90-degree hybrid. So the input comes over here and splits into two. And then we have an isolated port, which is reciprocal of that. The signals from here, 0 and 90, can combine in the isolated port. So what you can do is you can put two adjustable or tunable impedances at these two ports, and by adjusting them you can change the reflected phase of the signal, which then add up in the isolated port. You can get a lot of phase shift as a result of that. Now normally those two adjustable loads are in tandem, but I'm only using one here because I only have one to do this experiment with. So I've simply terminated the other port into a perfect 50 ohms, so there will be nothing reflected here. So essentially what we will have is the input will come over here, experience a 90-degree phase shift, go through this tunable component here, which I'll talk about, and then whatever comes back is going to be at a different phase arriving at the isolated port. Now the impedance, of course, is going to change the amplitude as well as the phase, so we want to investigate that. At the end of this tuner, I also have a 50 ohm impedance. Now this tuner has 3 stubs, and I can adjust and move these stubs out, like so. And by doing this, I can change the impedance. You can see there's 1, 2, and 3. They all have a maximum of the same length. Now, one of the very first thing we need to do is, instead of measuring it all together, is to measure just the tunable impedance here and figure out what are the surface areas, which parts of the Smith chart can we even cover with this, so we can get an idea of how useful it is. So let's measure first this component. And on the left, we have a live view of the tuner, so that when I adjust it, you can see the different effects and correlate that with the live view of the instrument we have here on the right side. Now I'm measuring a fairly narrow frequency range between 12.7 gigahertz and 12.8 gigahertz. That's only 10 megahertz. So I can see very clearly the impedance at that frequency. Now I can change that range, of course, but the impedance is also a function of frequency itself, especially as soon as you start adjusting the tuners. So that's why I've chosen a narrow frequency range, and it gives you some appreciation how difficult it is to make this phase shifter in reality a broadband phase shifter. 10 megahertz is really, really narrow, and this frequency is of some interest to SATCOM, for example. So let's see what happens. So here we have S11, right? So we're looking only at the return loss on this one cable. Now this doesn't really tell us much about the vector of the impedance. It only tells us the magnitude. And if I look at the measurement setup, or I should show under measure, you can see that the format is log magnitude. So I want to change that so we can look at it on the Smith chart. Now over here, there's a lot of different kinds of measurements you can make. We'll take a look at some of this. But let's go back and let's choose Smith chart. There it is. So right now at this frequency, we're sitting at 61.6 ohms and minus J2.4 ohms. So it's a little bit capacitive, but it's essentially basically almost 50 ohms. That's why the S11 was about -20. It wasn't so far above 50 ohms actually. So that's because these stubs are very, very short right now, and they don't make much of a difference at this frequency. But I can go ahead and adjust that and see what happens. Let's go ahead and try playing with the first one and see how it moves the impedance across the Smith chart. Let's see what circle we can cover. So if I slowly pull this out, you can see that I can change the impedance. I can make it quite inductive. At the very, very top over here, it's really inductive now. And you can see the impedance is almost 0. It's 1.6 ohms. And I can go over here. The resistance was almost 0. And I can bring it back essentially to where it was. I can even make it a little bit closer to 50. I'm making it, there it is. It's almost ideal here. And it's going to cover that circle over and over and over again. There we go, as I do this. Okay, so that's that circle. Let's go to the next one. And that's going to cover a slightly different one. You can see I can bring it all the way here, make it a fairly large impedance, almost an open circuit in this point. And we go over here, you can cross that 50 ohm one more time. And this is the circle of this one. And for the next one, we're covering yet a different circle. Right? So we have 3 circles we can cover. And of course, all of these can be combined. So if I bring this over here, and then I move the second circle, then I cover a circle around where that one stops. If I move it over here, and I move the third one, I can cover yet a different circle. So with the combination of this, I can cover a reasonably broad range of impedances on the Smith chart. But this one on the right seems to be the most sensitive, closest to the input. So let's try out this one. There you go. So that's the kind of circle we covered. Now this is pretty important for our phase shifter because it tells us the nature of the impedance we can change on one of the coupler ports. So now let's go and do exactly the same thing, connect this to the coupler and try it again. Okay, so now we have on the left the fully assembled reflection type phase shifter, and we have our port 1 connected here and our port 2 connected here. So what we expect from this phase shifter is a fairly constant response from port 1 to port 2, because you don't want the amplitude of the phase shifter to change, you only want the phase to change. So we have to look at those 2 parameters at the same time. And we're going to adjust these tuners based on what we learned from the first experiment to get the right circle in order to change only the phase of this phase shifter. So right now we're looking at S11 still. This doesn't help us very much, although by looking at the S11 and seeing that port 1 sees almost a perfect match should tell you about whether this is set in the correct position. And of course it's not, because it tells you that there's going to be nothing coming out of the other port. Well, we can verify that. Let's go and change the number of traces. Let's put 2 traces here. And you can see now at the bottom we have S21. S21 is at -23 dB. So basically everything's being absorbed into the coupler and into these 2 resistors, 150 ohm here, 150 ohm here. That's because this tuner in this position is almost 50 ohm as well. So nothing is going to come back out of the isolated port. This is not the condition where you can get phase shift. So we're going to adjust that. Also, we don't want to look at S11, so let's select this trace at the very top and let's change the trace. Instead of measuring Smith, let's go to measuring unwrapped phase. Okay, and we're going to change that from S11 to S21. So now at the very top we have now the phase of S21, and at the bottom the magnitude of S21. So keep your eye out on this number and on this number, which are the phase shifter performance numbers. So I'm going to play around with this until we get this to about -6, which is the best I can expect, because one port of this is now permanently connected to 50 ohms. It's going to absorb half the power, of course, and there's going to be the other losses from the other side. So let's go ahead and adjust that, and let's see what happens. Let me put this here. All right, I'm going to adjust the middle one until we get S21 to be about -6 or -7, which is the best we can do. There's some additional losses, of course. Let's see, there's -7. There you go. I think this is roughly the best situation. Now I'm going to keep this one fixed, and I'm going to adjust the second one, and now keep an eye out on the phase response and the magnitude response at the same time. So we're at 32 degrees, and look what happens. I'm going to slowly phase shift. Look at that. I've already phase shifted more than 60 degrees. Now there's going to be some change to the bottom one, but not that much. And I'm going to keep repeating those phase shifts. So I have a fairly long range of phases I can go through. And the more I pull this out, of course, the more phase shift I'm going to experience. It's going to reset back. There we go. Look at that. I now have a phase shifter, and it has quite a broad range of phase shifting. Look at that. That's pretty amazing, right? So we do have S21 changing a little bit, of course, but not so much. And it's exactly what you want. You want a roughly constant amplitude, and you want phase shifting. There it is. Now, I'm not proposing that this necessarily is how you should build this phase shifter, but the concept here is being demonstrated, where we're using the reflection of a tuner combined with a coupler to create a phase shift. But I also want to point out how easy it is to use the FieldFox. It is specifically designed with very few buttons to access some of the settings of what you want to measure. And that's because this is supposed to be a one-handed instrument. You're in the field, you're holding this with one hand, and you only have the other hand in order to reach to the settings. And you want to do this as quickly as possible, because you may be on top of a tower or in some harsh environment, or for example in the desert doing some military operation. You want to looking for some signals, or you want to measure and tune your antenna. So they've done a lot of work on making sure the firmware is easily accessible, and there are tons of settings in the S-parameter network analyzer function. Now next, let's take advantage of the Keysight FieldFox capability to interface with external power sensor modules, like a USB one that I have over here. This is a Keysight U2000A, which is an 18 GHz power sensor connected with the USB directly to the FieldFox. Now the FieldFox has an app inside that allows you to use itself as a power sensor. It uses the spectrum analysis capability and integrates power over a particular band that you're looking for. But if you want really precise external sensors, you can also use that by connecting it through the USB port. So what we have here is a power amplifier on the left side and a bigger power amplifier here on the right side. This is a classic situation when you cascade multiple power amplifiers to increase the total external power. The output of the last power amplifier is terminated into a high power resistor here at the end. So the problem here is typically interstage matching. You don't know what the impedance of this one is, and you don't know what the impedance of this one is, and even if you measure them, you need some kind of a transformation between the two. Here we have again the tuner in the middle, so we're going to use that to adjust the interstage matching to optimize the power transfer from this power amplifier into this one. And in order to aid with that, we have a power sensor which is connected to a coupler between the two of them. So any power reflected back over here finds its way into the power sensor. There's also a 20 dB coupling factor over here, which we need to take into account. So if we minimize the power measured over here, we have done a good matching between these two, and we maximize the total power transfer between the two amplifiers. So we're going to use the application of the power detector in here to take advantage of that. But we can actually take it a step further. So not only the Keysight FieldFox can act as a power sensor, it can also act as our source, because it has a source function built into it. We can turn that on coming from channel 1. That's exactly what's connected over here. So we're going to excite this system with the same center frequency we have set the power sensor to. And that's a huge advantage, because all of this experiment is actually done using a single instrument now. We're using this both as the source as well as the power detector capability. And all the power supplies are up here. Of course, we're running the first power amplifier, second power amplifier from here. It's not turned on yet, but I will do that in a second for our experiment. So let's go and take a look at the screen. Okay, so again, on the left side, we have our live measurement setup. The power supplies have both been turned on, but there is no power going into our amplifier. So as a result, when I load up the application for measuring the power sensor, we're seeing absolutely nothing. This is basically the noise floor of this particular power sensor that we have. Don't forget that there's also a 20 dB coupling here as well. So I want to turn on the source so we can see the effect of this tuner and the mismatch between these two different amplifiers. Now, one additional point I wanted to bring up is that you can, in fact, change the kind of power sensor you have to a LAN as well. We're not using a LAN power sensor, but you can connect over the Ethernet. So under measurement, we're measuring average power. You can also do things like gain and RX power too. Because you have a source, you can calibrate out the source or the cables, and then you will have gain measurements. It will be a scalar measurement, which again is not surprising because you have control over all of those things. So let's go ahead and turn on the source first. We go under sweep, and here's our power setup. And you can see that I have the source power set to 0 dBm. I really want to drive the input of this amplifier fairly hard so we can see the load pull condition, and we can see what happens in worst case scenarios when this guy is running really non-linearly, and then we want to find out a large signal matching condition between these two amplifiers. Let's turn it on. And as soon as I turn it on, you can see that we're measuring minus 2 dBm. Now, minus 2 dBm is a lot because there is also a 20 dB coupler in here. So there's a lot of power being reflected back, almost all of it, which is quite bad. So let's see how much we can improve this. I'm going to start from here. Oh, that makes it worse. Let's start from here. Oh, okay, we're getting better. That's pretty good. There you go. We improved it by quite a bit. Let's go to another point here. And continuing, let's see. There we go. I think that's pretty good. Yeah, anyway, you can play around with it a little bit more. But you can see that what I did was I basically tune these two amplifiers together, now we have a much better reflected power situation, which means that the amount of power we're delivering to this final load is now nominal. Now this is a typical procedure you can also go through for load pulling a power amplifier and get a whole bunch of additional information. All of this, remember, is contained within the FieldFox. I'm using only the FieldFox both as a source as well as the power sensor. So because the Keysight FieldFox is equipped with a two-port network analyzer, there are a lot of emerging applications you can write on top of that, which rely on the vector measurement capability of a two-port network analyzer. So there are essentially other ways of representing the S parameters. Things like TDR, for example, allows you to measure things that are things like distance to failure, distance to fault. If you have a cable that might be broken somewhere underground and you want to find out where that break is, you're essentially looking at S parameters, but represented in a way that's useful what you're doing in the field. A lot of these things can give you a lot of productivity improvements. There are other things you can do. For example, the vector voltmeter is quite advantageous if you want to measure and trim cables or measure the phase and magnitude difference between 2 points in a system. Again, this is of course network analysis, but represented in a way that you can use very easily. So I won't go through that because it will take forever, but I think we should turn our attention now to the spectrum analyzer mode, because this is yet a completely unique capability that allows you to do spectrum analysis as well as real-time spectrum analysis, which is even more interesting in an instrument of this size. Let's give that a try. So next we're going to use the spectrum analyzer feature, but it also has something else built in it which I personally really like, and that is the ability to have a synthesizer function inside of the FieldFox. But the key here is that that synthesizer is entirely independent of where the sweep frequency is in spectrum analyzer mode. So for example, you can do your spectrum analysis on this port anywhere between DC to 50 gigahertz in this case, but you can also assign a CW tone to the other port at any frequency you want. You can have it tied to the sweep, you can have it independently at some random frequency, you can have it at an offset frequency for mixer measurements, and that's not something you often find. And that's because the only way to make that happen is to have more than one synthesizer that's independent inside of the FieldFox, so you can route the sweep synthesizer differently than you do the CW tone coming out. That's pretty significant. First, we're going to take a look at that signal and see the quality of the CW coming out. Of course, we can't expect something like a full-size synthesizer, but nonetheless, this makes essentially this unit a 50 gigahertz synthesizer and a 50 gigahertz spectrum analyzer fully independently in the same box. So let's take a look at the quality of that signal. So let's take a look at the signals. I'll be using a Keysight MXA. Now, the MXA version that I have only goes up to 26.5 gigahertz. So that's the maximum we're going to be able to take a look at, but it's going to give you a good idea. Now we're going to try starting at 500 megahertz CW tone. That's actually the hardest situation because there are a lot of harmonics that will be in band, as you will see. Let's go, turn it on. There we are. So you can see we're looking at all of the harmonics of 500 megahertz, starting with the third one being the largest. And we have a THD of about 10 to 12 dB or so, and the output power is 0 dBm. Now as you increase the frequency, this situation gets better. Here's 1 gigahertz. 1.5, 2 gigahertz. You can see the harmonics certainly move away from each other as to be expected. The THD is a little bit better. We're going to continue. Here's 4 gigahertz. And here is, let's say, 7.5 gigahertz. Let's go to 10 gigahertz. Here you go, 10 gigahertz. So of course, we're not looking at some of the other harmonics here because the frequency limited here is 26.5 gigahertz. But we can continue on. Let's go to, here's 26 gigahertz at the very edge. The loss that you see is primarily from the cable. But yeah, I mean, this is a fully independent synthesizer that I can do whatever I want with. Now, you may or may not care about the spectral purity depending on what you do. At very low frequencies, it's probably more important to you. But I would say that given that this goes to 50 gigahertz, it's exceptionally valuable to have this as a standalone synthesizer. And we're going to use that in our next experiment. Now, if I have to criticize something about the Keysight FieldFox, it would be the sweep speed in spectrum analyzer mode. We're looking right now from DC to 50 gigahertz and a resolution bandwidth of 5 megahertz. That's going to give us a particular displayed average noise level. Now, if I want to lower that, I have to lower the resolution bandwidth. We can try that. Let's go ahead and lower it to 300 kilohertz. And as you can see, it slows down quite a lot. Now, if you're looking at a narrow frequency range, you probably don't care so much. But if you're looking for a signal that could be jumping around across multiple millimeter wave bands, this is just a little bit too slow. If they improve that, there's really not much to complain about the FieldFox. And I'm going to show you, let's try and change the span a little bit so you can see that it does indeed get quite a bit faster. Let's try it at 50 gigahertz, for example, and change the frequency span to, let's say, 5 gigahertz, right? So you can see that it, of course, speeds up quite a bit, but still, I would like to see it be much, much faster so that you can hunt for interference and things that you don't know where they are across a wide frequency range. So here's the setup of our next experiment. What we have here is a 5G super heterodyne transmitter. It operates at around 24 gigahertz, which is one of the lower frequency bands for 5G applications. We're getting our LO directly from the FieldFox, going over here with an amplifier here to boost it to above 10 dBm, connecting it to a triple balanced mixer over here. This is a millimeter wave mixer, and it has an IF coming from our first stage IF transmitter. This IF is at 2.4 gigahertz, gets up converted to 24 gigahertz, and then it gets fed back to our FieldFox. So essentially, this super heterodyne transmitter can have a lot of impairments. We're going to take a look at some of those, especially because we have a digital IF transmitter and we can emulate a whole bunch of different kinds of failures. So let's go ahead and see what the spectrum coming out of the system looks like. So in our setup on the left over here, the IF is enabled, but not the LO. So we expect to see something coming out of our mixer, which represents the IF to RF isolation. And that you can see indeed shows up around 2.4 gigahertz, which is where we expect it. But the signal is coming and going. Every time a sweep is completed, sometimes it's there, sometimes it's not. So something is wrong with the IF source. Now we could investigate it directly over here by taking advantage of the leakage. But really what we want is at the RF output. And in order to see that, we need to turn on the LO. And I said we're going to use the FieldFox itself to generate the LO. We go under source over here, and you can see that the source CW frequency is set to 22 gigahertz, and the source power is -5. I have an amplifier after that. When I turn this on, the LO will come over here through the amplifier, and it will hit our mixer. Now, by the way, if you go under advanced, you can see some additional functions that you can have and different kinds of source mode that you can provide, which is really handy depending on what you're measuring. So we're just going to keep it at a constant CW, which is convenient. A coupled CW would place the tone at the center frequency of what you're looking at in the spectrum analyzer. Also really handy little software trick. Let's go back over here. Let's turn the source on. Now, as soon as I turn the source on, we can see it right over here. This is now a LO to RF isolation limitation. This is a CW tone, so you can see it's always there. There's nothing wrong with our LO signal in this case. But the IF signals all come and go, so there's something wrong with the IF, and if it's wrong, it's going to show up on the upper and the lower sideband at our RF output too, which is exactly what we are seeing. So I'm interested in mostly looking at the upper sideband. You can see there's some gain drop here, but that's okay. For our purposes, we're looking at the 24 gigahertz. So let's go ahead and center our frequency there. We can adjust that very easily. Go into frequency, change the center to 24.445312 gigahertz. Okay, and we can change the span. We can look at a 100 megahertz span. So when you're dealing with an IF signal that has some impairment, depending on how you look at that IF is going to be the quickest way to find out what's wrong with it. So a variety of analysis tools need to be available to you. Now there's a whole bunch of them built into the FieldFox. We're going to go over here. I'm going to go on to interference analysis. I'm going to turn on the spectrogram for a moment. And with the spectrogram, we can see all these variety of jumping of the IF signal. Now you may think that this could be some kind of an FM modulated signal, or that the signal could be jumping in frequency. And that's certainly a possibility. But that's not the only way this could happen. For example, if your signal has some modulation on it, AM on it, it can also show up as frequency shifting around if it's rapid enough. So we still don't exactly know what's going on with it if you look at the spectrogram alone. We can also look at it in a different way. There's also another source of interference analysis, which is this waterfall, which I quite like a lot, and gives you kind of a 3D view of what's going on to the signal. If you look at it, you can see that tones occasionally disappear in this waterfall view. So something might be happening to the amplitude of our signal. And for that, we need to look at the signal at a much higher update rate. By the way, the screen of the instrument is updating faster than what you see here. This remote display is indeed a little bit slower. So this helps, but really what you want is the real-time analysis or some kind of IQ analysis on this signal to really find out what's going on with it. And in that mode, we're going to switch to the IQ analysis mode. If I go over here and click on more, one more time, we have IQ Analyzer. I can click on that. Now, as soon as we go into the IQ Analyzer, we have a brand new application that's loaded, and we can try and figure out the signal there. But unfortunately, for some reason, the source control capability is absent in the IQ analysis and the real-time analysis. And I don't think that's anything really a limitation of the instrument. It's just a limitation of the firmware, I believe. And I really hope that they add that to it, because as soon as I switch out of the spectrum analyzer, I can no longer control the source. And that's unfortunate, which means I'm going to now have to use an external source to do this. But let me switch that. We can come back and do our analysis again. Okay, so I went ahead and I switched our LO. You can see it's now going to the left, so it's coming from a different synthesizer. It's still at 22 gigahertz. But now we're looking at the same center frequency we were looking before, and we can see our signal coming out of the RF and something's going on with it. So let's change what we're looking. Instead of frequency domain, let's look at the time domain of the signal. I'm going to look in particular to the RF envelope of the signal. And there it is. And this should now already tell us everything we need to see. So let's make some adjustments on the sweep. So let's look at a slightly higher time. Let's say maybe look at 500 microseconds worth of sweep. There we go. And let's set some trigger here so that this stops moving around. I'm going to give it a trigger. I'm going to do a video trigger. Okay, and then we can set our trigger level. It's actually already set to minus 25 dBm. And there it is. And that is what's going on. So this is basically a switched IF system. The IF comes on for a short amount of time, and then it turns off, and turns back on, and turns back off, and it's just got this square pattern here. So this is an IF that was turning on and off. But because it was turning on and off fast enough, it emulates some kind of an erratic AM modulated signal coming from the RF port, and that's why it was showing frequency content that was jumping all over the place on the waterfall view. And that's why it's so important to have real-time capabilities and IQ capabilities directly on the waveform. So that's one of the advantages of this feature. But let me go ahead and change our impairment to a slightly different kind of impairment so we can see the real-time spectrum analyzer function as well. And now we're looking at a different kind of IF impairment. We're looking at the frequency domain again, and it doesn't look like there is anything wrong. We can see a CW tone actually coming out, and it's sitting somewhere in the middle of the screen. So what's going on here then? Does this really mean that this is a simple CW transmitter? Well, the only way to find out is to look at it in real time and see if it does have any problems that are hidden by the method we're looking at it now. So let's go under mode. Let's go under real-time spectrum analyzer. So now we have extremely fast update rate. Now this again does not do it justice. I'll try and see if I can put in a video actually of the instrument. This is much faster in reality. So here's the screen of the instrument directly, and you can see how fast the update rate is. And indeed there is a problem. You can see every second there is a shift in the CW tone, and it jumps up to a higher frequency and jumps back down. And at the top you can see that the 100% probability of intercept is 13.3 microseconds, and the minimum detectable pulse is 47 nanoseconds. And it's really important to look at this screen directly on the instrument. I'll show you what it looks like in the remote display. And this number over here, this does not apply to the remote display, only to what you're looking at here on the instrument. So with the real-time spectrum analyzer, we can catch that fault. And here, of course, you can see that we don't catch that tone as frequently as we would when we were looking at the screen itself. But what I can do is I can change the persistence, and I put it to infinite. And if I do that, then we can very easily catch that event, because the infinite persistence is applied to the instrument and not to the remote display. So we will immediately see the problem. And right away, you can clearly see the two tones that we were talking about. Let's go ahead and turn this back off for a second. I can also measure, let's cancel that. I can also measure the spectrogram. And the spectrogram, you will indeed catch that. There it is. That was one that just passed by. Here's another one. Here's another one. So we can see that there is a problem, that frequency hop can be captured using this as well. But of course, when you have a real-time spectrum analyzer, there is a lot more you can do, and probably one of my other favorite features is that this instrument is fully VSA compatible. So we can do complete demodulation and take advantage of the richness of the VSA software to do all kind of analysis. Let's go ahead and set that up so I can show you some demodulation examples. And now we're going to use our little 5G prototype transmitter to do an actual modulation experiment. I have removed the little board that we had here, just used to be our IF board, and I have replaced it with an instrument now. I've replaced it with a Keysight M8190A, which is a dual channel arbitrary waveform generator. I've done a review of this instrument as well, and it's connected to an embedded controller, and this screen is something that I have added to this instrument. It's just basically showing me the window that I can configure the ARP with. Now I've configured the ARP to do a digital up converter, which is one of the features of this device. Allows me to modulate around a certain carrier. I'm doing that at 2 gigahertz. So we have a 2 gigahertz IF coming out here, and at that 2 gigahertz IF, there is a 75 megasymbol per second 64 QAM signal around that. So that's going to get up converted here but our mixer down here, that's going to come out at 24 gigahertz. So because we have VSA compatibility, we can go to the VSA software and see what we get. And here we are on the VSA software. You can see that I have configured the FieldFox through the Ethernet to connect to the VSA software. This was really painless. It worked right away. Didn't have to do anything, just enter the IP address. Here we are. Here's our modulated signal. It's being demodulated here. The carrier center is 24 gigahertz, as you can see. We're looking at a span of 100 megahertz. And because we have a 75 mega symbol per second, and with a particular pulse shaping, it's occupying almost the entire bandwidth. So this doesn't look that great. That's because there is some bandwidth limitation and some intersymbol interference coming from the transmitter. And we want to equalize that. We can of course do this because this software does have equalization built into it, among many other features. There you go, here's our setting. You can see 64 QAM, 75 megahertz, and I'm looking at 4096 symbols to ensure that we get a really nice and realistic EVM measurement. Under compensation, let's go and turn our equalization on. I'm going to reset the equalizer. Oh, it's going to calibrate now for a second. This has to do that every once in a while. There it is. Look at that. It's cleaning all that up. That's because it's mostly dominated by ISI. I'm going to let that run for a little bit. And this gives us a very nice view of what the equalization looks like and what the channel response looks like. I'm going to go ahead and pause the equalization here. Let's put it on hold. There we go. We can keep it there. So we can see the impulse response of the channel. Not a lot of reflections coming back, which is nice. And look at that. We can see a tiny bit of phase noise on the outside. That's because we're up converting using another synthesizer. So we have three sources of phase noise on top of each other in this constellation. There's the phase noise of our 22 gigahertz up converter, the phase noise of the ARP, which is very small, and the phase noise of the FieldFox, which is also not too bad. And that's the combination. Very nice constellation. We're at about 2.5% EVM. Now the raw constellation, the lowest EVM we can measure with the FieldFox is well below 1%. If there's nothing in the way, we can go to 0.5%, no problem. So this is primarily the limitation of our transmitter, which is pretty nice to see. And all of this compatibility with VSA, I have covered it in the channel before. All of that is available. You're basically dealing with a 100 megahertz channel that you can put anywhere from DC to 50 gigahertz and analyze with the VSA. So next, let's measure noise figure using the Keysight FieldFox. Now the noise figure personality on this instrument actually goes beyond what most traditional spectrum analyzers are capable of doing. This instrument can also calculate noise figure uncertainty, which can be quite helpful. We'll talk about that in a bit. And of course, you can measure noise figure all the way to the maximum specified frequency of the instrument, in this case 50 gigahertz. Now the setup that we have here is going to allow us to investigate the influence of a resonance circuit in front of a low noise amplifier. We're going to also swap them at some point. We'll take a look and see what happens in that situation. So we have our noise source here on the left, which is an Agilent T346C. This is a 26.5 gigahertz noise source. And the 28 volt required to run the noise source comes from the DC voltage port of the unit, which is programmable for other purposes, but this is a clever use case of it because you can also turn 28 volt on and off on this to get the noise source running. Here's our resonance tank, which we can adjust, and then our low noise amplifier operates between 8 to 11 gigahertz, and the output of that is connected to the input port of our FieldFox. At the same time, we have, of course, an Ethernet port coming out, which is nothing unusual. So we're going to take a look at the software very carefully. Now, above this, we have our power supply. That's just simply running the low noise amplifier. There's nothing else connected in this setup. Now, it's really important to get this setup originally built very carefully because you require an instrument calibration. I'll show you the wizards built into the noise figure personality that walks you through this. I've already obviously done that. I won't waste your time with it, but I'll show you how it would look like on the unit. Let me also show you a little attention to detail from Keysight. So when you enable the DC voltage output, a little LED turns on inside of the unit, which illuminates the connector. Because if you're out in the field and it's dark outside, you want to be able to see where you're plugging this connector into. Again, these little tiny things make a really big difference in the usability of an instrument like this in the field. And here we have our live measurement setup on the left and the screen of the FieldFox on the right. Now I've already selected the noise figure personality, which you can reach by pressing mode and then going through all the options we have available, and here's our noise figure. The very first thing, as I mentioned, you have to set up your noise figure measurement. If I go under measurement setup, there's a couple of important things. The most important is the noise source. You have to define what kind of noise source you're using. Now here's our noise source already connected. That's because I've already done the calibration. Now, if I click on noise source, I can edit the ENR table of this particular noise source. I've already saved it and we can edit it so we can take a look and see what kind of information there are. So here's the model number and the serial number. I also have entered some ENR uncertainty. Now this is pretty important because the uncertainties entered here can be applied to the entire ENR table, and that can be used to highlight the total noise figure uncertainty calculation. Let's go a little bit further down and see what we have here. So for instance, I have entered all the ENR values of the noise source starting from 10 megahertz all the way up to 26.5, and I have just indicated that all the ENRs have an uncertainty of 0.1 dB. That's of course not necessarily true. This is an old noise source anyway. This is just for demonstration. But I also have put that the gamma coefficient when the noise source is off is 0.2. This means that there is a difference in impedance of the noise source when it's on, when it's off, in the hot and the cold state. This can be quite important as well because it changes the way the device under test sees the noise source. That the impedance mismatch adds uncertainty to the noise figure itself. All of that can be used in the instrument to calculate the overall uncertainty of the noise figure. This is a pretty sophisticated calculation. You can of course do it offline, but this is built into this unit, into the noise figure personality, which can be really handy. So now that we have all of the SNR value, the ENR values already entered here, I'm going to just click done. So we have that saved. The next thing you need to do is define what kind of device under test you're measuring. Now in this case, we're measuring just a basic amplifier. So you can see the block diagram of it is exactly the block diagram we have here on the left. We have our noise source and the device under test going into port 1, which is exactly what I have here. Now you can also have other things like down converter, up converter, and a multi-stage converter. And selecting each of these will change this block diagram, and then it will guide you through how you should be setting it up. In this case, we actually have the simplest situation because we're just measuring an amplifier. If I go back over here, we go under sweep. Oh, no, gotta go under next. And we're gonna go done here. There we go. Now if I go under sweep, you can see that I'm measuring with 21 points. You can increase that. We will have to do this to see some subtle measurement details here. But if I also go down and measure, right now I'm looking at the gain of this amplifier. So you look and see we have just under 35 dB of gain from 8 gigahertz to 11 gigahertz, which is exactly how much gain this amplifier should have. Now, despite the fact that we have this tunable resonance in front of the amplifier, we don't really see anything. And that's because the number of points we have is not high enough to find out the effect of this on the gain of the amplifier. But more importantly, we are interested in measuring noise figure. You can measure noise figure or noise factor. They're just conversions of each other, as well as noise temperature, of course. You can also extract the Y factor directly. It is, after all, using Y factor to measure a noise figure. So let's click on noise figure here. There's a noise figure. So it's at about 3 dB or so, which is exactly correct for this amplifier. That includes everything from the tip of this noise source all the way to the input of the instrument. Now, I have already marked on this the noise figure uncertainty, which you can turn on and off. If I go under measurement setup, we go under uncertainty, you can see that we can define our device under test uncertainty, the preamp, as well as what variations or different kinds of uncertainty contributions you want the instrument to take into account. Right now I have turned everything on, so the jitter uncertainty is there, which is the integration that's already entered as part of the setup of the unit. The ENR uncertainty which we entered and the mismatch uncertainty which we also entered. There is no user cal uncertainty here, is turned off. So these markers tell us what is the possible range of noise figure it can actually be within a certain Gaussian distribution. And that's pretty useful because it tells you if you're going to report a noise figure of 3 dB, you have to report the range in which it can be because of all the additional sources of uncertainty we have in the setup. This is pretty useful and can be often something that's missing in a lot of noise figure reported results. Let's go back over here. Let's turn the noise figure uncertainty contributions off. There we go. So we can only see the basic noise figure here. Now, if you notice, I don't see anything that's the effect of this resonance. What we need to do is to increase the number of points so we can catch this effect. So let's go over here under measure. Let's measure the gain once more. And I'm going to go under sweep. I'm going to change the number of points from 21 to 10 times higher to 201. And here we are with the additional points. We can see some interesting features in the gain emerge. So there is indeed a dip here, and we want to check to see if this dip is correlated with our resonant tank here. And there's also a little bit of additional ripple, which is also because of the mismatches of this entire chain sitting before the amplifier. So that drop, if that drop is due to this resonant in the front of the amplifier, this is going to directly contribute to an increase in noise figure because the loss is in front of the amplifier. Well, we can verify that. We can go ahead and measure noise figure, and we can see if it does indeed do that. And check it out, our theory was correct. There is a peak in the noise figure exactly at the same frequency where there was a drop in the gain. And this is, significant. It's about 1.5 dB increase in noise figure, and it's very narrowband. That's because the quality factor of this resonant tank is very, very high, and that's why you see such a sharp increase. If I increase the number of points further, you will see even a better shape of this. Now we can change the frequency range to focus around this a little bit more. And here is a zoomed in version. We're looking from 8.5 gigahertz to 9.5 gigahertz now. Again, 201 points. And I have the peak marked here with a marker. It's set to 9 gigahertz. The noise figure is 4.6 dB. And let's check to see if that's correct. I'm going to go and lift this unit here, bring it closer to the camera, and then see if it matches what we're supposed to see. Check it out. How's that? Amazing. That's exactly where this is set to. So that's what we expect to see. Because the resonance tank is at 9 gigahertz, a portion of the energy entering the system is absorbed by this, which is equivalent to increasing the noise figure, reducing the signal to noise ratio, and that's exactly what we see. So now I went ahead and I swapped the two units. I put the amplifier in the front, directly connected to the noise source, and our little resonant tunable tank here right after. So we still have the same chain of amplifiers. The order is just reversed. So if I look at the gain, again, we see exactly the same dip in exactly the same location. That's not surprising. These are linear cascaded blocks. So of course you're going to see the same gain. But what about the noise figure? Well, let's go take a look at that. I'm going to measure noise figure now. Let's see what happens. We already passed the middle. Take a look. It's completely flat. That little peak that used to be there, it's gone. But again, that shouldn't also surprise us. This is, of course, Friis equation for a noise figure of a cascaded system. The noise of later stages is divided by the gain of the stages in the front. That's why in the system, the noise figure is determined by the first amplifier in the stage. You don't want to have loss in front of it. But this is also a classic problem with any cascade system. If you put your losses in the front, you improve the linearity of the system. If you put your losses at the end, you improve the noise figure of the system. And this confirms Friis equation for us, of course. Look, totally flat noise figure across. I also want to show you one other thing, just for completion. If I click on Cal here, I can go under the calibration, and you can see that I can rerun the calibration, and it just tells us how we should connect it. I'm showing this for the sake of completeness, so you know that this is how I performed the original noise source calibration. And there you go. This was hopefully a good overview of what the noise figure personality on this instrument looks like. A lot of capabilities. I've already really covered a little bit of it, but it's a full-fledged noise figure measuring instrument. And there you have it. I hope you enjoyed this review of the Keysight FieldFox Microwave Analyzer. And there's a lot more yet we can do with this. I will make more videos in the future exploring some of its other software capabilities, and I'm sure there will be even new ones coming out. And I know what you're asking, where is the teardown? Now, it's very hard to get a hold of the actual internal boards of this. Right now it's going to be quite difficult, but I'm working on it to be able to do a teardown and analysis of what's inside this, because it's so compact and everything has to be there, all these independent synthesizers, and the isolation in something this size must be a nightmare. So they've done a fantastic job, and I may get to see it. As I said, there are some improvements that can be made to it. Certainly some corner cases in the firmware can be improved, but overall, if you're going to be out in the field and you want to do pretty much everything in a handheld device, this is a really hard one to beat. I hope you enjoyed this. If you do purchase one of these, nothing comes to me, of course. This is all independent, but please let Keysight know that you watched this video and that you benefited from it, so that I can get a hold on these wonderful instruments in the future. We can demo them here on the signal pad. As always, I'll see you in the comment section.